Start with the name of Allah Almighty, who is most merciful and most beneficent. Our final year project title is Simulation and Fabrication of Symmetrical and Asymmetrical Airfoils using Ansys simulation at different wind velocities. We have a group member of 2 students, Muhammad Zakaria, me, and Zabiullah. We are very thankful to Engineer Shakib Jiskani for supervision of this project. And we are also thankful to our co-supervisor, Sir Engineer Ghulam Akbar. This is the introduction of our final year project. Wind turbines were designed by engineers to convert wind energy into useful electrical energy through mechanical generators. In order to get maximum efficiency, researchers put much effort into the design of effective blade geometry. In the early stage, the airfoils of helicopter were used for wind turbine blade design. Now many specialized airfoils have been invented and used for wind turbine blade design. So we are using wind turbine to convert the kinetic energy of wind into rotational energy, and then that rotational energy is converted into electrical energy by using the mechanical generators. If the wind turbines blades are not compatible to the wind velocity, then the obviously efficiency of wind turbine can be decreased. This is the motivation of our final year project. The main motive of this study is to investigate the aerodynamic performance of different airfoils used in wind turbines, how different airfoils will behave at different wind speeds, how angle of attack will affect the performance of airfoils, how to maximize the efficiency of wind turbines. Obviously, this is our main purpose, main motive. Our main motive is to increase the efficiency of a wind turbine. These are the types of airfoil for study. First one is symmetric airfoil, and the second one is asymmetric airfoil. These both are of 2 different types. What is symmetric airfoil? Symmetric airfoil, it is the type of airfoil that has the same shape on both sides of its center line. If we look at this airfoil, this is the symmetric type of airfoil. This is the center line. It is also called length. If we cut this airfoil into 2 pieces from center, then it converted into 2 same shapes. So such type of airfoils are called symmetric airfoil. Asymmetric airfoil, it is the type of airfoil in which the shape on both sides of the center line are different. If we observe this airfoil, this is the asymmetric airfoil, and we cut this airfoil into 2 pieces from center line or from chord length, then it does not cut into 2 same shape. So this is the problem statement of our final year project. Airfoils have a great impact on wind turbine performance. If the airfoil shape is not compatible with the wind velocity, then the efficiency of wind turbine will be minimum. Suitable airfoil shape for minimum wind velocity requires a comparative analysis of different velocities, different airfoils. This is the literature review we have done throughout this project. First one title is Comparison and Selection of Airfoil for Smart Wind Turbine between NACA and NREL series airfoils families. And the details of this paper is NACA airfoil contribute more in low wind speed that we observed in our this project also. And NREL airfoils are better suited in stability criteria. We also observed this statement in our project. 2D numerical simulation study of airfoil performance. This is the title of second research paper that we followed. The lift coefficient detail of this paper is the lift coefficient and the lift force increase with the increase of air velocity. NREL airfoil families for art. This is the title for third research paper that we followed, and the detail of this paper is NREL series of blades are providing large increase in annual energy production as a result of better lift to drag ratio. And this is the fourth paper that we followed in this project. The title of this paper is Comparison of the Power, Lift and Drag Coefficient of Wind Turbine Blade from Aerodynamics Characteristic of NACA 0012 and NACA 2412. And the details of this paper is there is a range of angle of attack where the lift coefficient varies linearly at some point. Maximum value of lift coefficient is reached where further increase in angle of attack. And the fifth paper title is Horizontal Axial Wind Turbine Blade Design using Ansys Fluent. And the detail of this paper, we get smooth calculation of aerodynamic forces on each element of the blade using the lift and drag coefficient result developed from the CFD simulation. These parameters can be used for practical applications. These are the aims and objective of our final year project. First point is to analyze the aerodynamic performance of different airfoils, symmetric and asymmetric at different wind velocities. And the second one is simulation of symmetric and asymmetric airfoil in Ansys to analyze the aerodynamic performance of different airfoils, symmetric and asymmetric at different angle of attack. This is the methodology of our final year project. This is the flow chart for this project. First, we have done with the literature review and then select the airfoil for study. And then we import the coordinates of each airfoil in Ansys for geometry purpose. And then we made the geometry of each airfoil and then mesh that airfoil. The purpose of meshing is to get good results. And then we connect the meshing to the setup. And we have done with simulations. After simulation, we analyzed each airfoil and select the best 2 airfoils from 10 different airfoils. And then we construct that airfoils in Solidworks for fabrication purpose. And at the last stage, we fabricated these best 2 airfoils by using 3D printing of Sakkara EPH University Fab Lab. These are the suggested airfoils we studied. First one is symmetric type, and the second one is asymmetric type. And symmetric type of series of airfoil, we choose NACA 0012, NACA 0009, NACA 0018, NACA 0006, NACA 0024. And from asymmetric series of airfoils, we choose NREL S825, NREL S834, NREL S822, NACA 4412, and NACA 2412. These are the geometries for different airfoils. This is the geometry for NACA 0012, and this is the geometry for NACA 0009. And this is the geometry for NACA 0006, and this is the geometry for NACA 0018, and this is the geometry for NACA 0024, and this is the geometry for NREL S825, and this is the geometry for NREL S834, and this is the geometry for NREL S822. And this geometry shows the airfoil of a NACA 4412, and this geometry is for NACA 2412. And this is the airfoil geometry we have made in Ansys. This is the meshing of airfoil that we have meshed each airfoil. For fabrication, these parameters are required for each airfoil that we fabricate. For NACA 0012, the chord length we selected, which is 152.4 millimeter. This is the because in Fluid Dynamics lab there is a testing airfoil for wind tunnel test. We select the chord length of that airfoil, and we also follow that chord length for our fabricated airfoil. And this is the depth or span of airfoil, and this is the thickness of the airfoil, which is 18.288 millimeter. And there's the NREL S825 chord length of NREL S825 is 152.4 millimeter, and depth is 52.4 millimeter, and the thickness is 26.0604 millimeter. This is the SolidWorks design for NACA 0012. We have designed the NACA 0012 in SolidWorks first for fabrication purpose. And using this file, we fabricated the airfoil by using 3D printing machines of a Sakkar IBA University Fab Lab. This is the SolidWorks model for NREL S825. These are the fabricated airfoils. This is the results and discussion portion. This table shows the result for comparison with velocity and lift coefficient for symmetric airfoils. If we look at wind velocity of 5 meters per second, NACA 0012 having a lift coefficient of 0.3971, and NACA 0009 having a minus 0.2300 lift coefficient value, and NACA 0018 having a lift coefficient value of minus 0.3320, and NACA 0006 having a lift coefficient of 0.3990 value, and NACA 0024 having a value of lift coefficient 0.1832. Same at 10 wind velocity of 10 meter per second, NACA 0012 having this value of lift coefficient, and NACA 0009 having a value of minus 0.2324, and NACA 0018 having a lift coefficient value of minus 0.2844, and NACA 0006 having a lift coefficient value of 0.4045, and NACA 0024 having a lift coefficient value of 0.1787. Same is the case for wind velocity at 50 meter per second, 20 meter per second, and 25 meter per second. The lift coefficient for different airfoils are given. This is the graph for velocity versus lift coefficient for asymmetric airfoil. This red line shows the lift coefficient value for NACA 0006, and this blue line shows the lift coefficient for NACA 0012, and this line shows the lift coefficient value for NACA 0024, and this line shows the lift coefficient value for NACA 0018, and this shows the lift coefficient for NACA 0009, which is the lowest lift coefficient, which is not good for an airfoil. This is the drag versus velocity table for symmetric airfoils. If we look at wind velocity of 5 meter per second, NACA 0012 having a 0.0024 drag coefficient value, and NACA 0009 having a drag coefficient value of 0.0738, and NACA 0018 having a drag coefficient value of 0.3020, and NACA 0006 having a coefficient value of 0.0124, and NACA 0024 having a drag coefficient value of 0.10. If we look at the wind velocity of 10 meter per second, NACA 0012 having a drag coefficient of 0.0053, and NACA 0009 having a drag coefficient of 0.0851, and NACA 0018 having a drag coefficient of 0.3186, and NACA 0006 having a drag coefficient of 0.0149, and NACA 0024 having a drag coefficient of 0.06006. At the wind velocity of 15 meter per second, 20 meter per second, and 25 meter per second, the drag coefficient are given for each symmetric airfoil. If we look at the graph, NACA 0018 having a maximum drag coefficient, and after NACA 0018, NACA 0009 having a drag coefficient, and this line shows the drag coefficient of NACA 0006, and this yellow line shows the drag coefficient for NACA 0024, and this blue line shows the drag coefficient of NACA 0012. If the drag coefficient is low for aerofoil, then that aerofoil is good for horizontal wind turbines. So here NACA 0012 having a low drag coefficient value, which is the best one. This is the results for velocity versus lift coefficient for asymmetric aerofoils. This table shows the velocity versus lift coefficient for asymmetric aerofoils. If we observe at wind velocity of 5 meters per second, NREL S825 having a drag coefficient, lift coefficient of 0.4756, and NREL S834 having a lift coefficient of 0.1531, and NACA 4412 having a lift coefficient value of 0.3306, and NACA 2412 having a lift coefficient of 0.1581, and NREL S822 having a lift coefficient of 0.1862. Same if we observe for 10 wind velocity of 10 meters per second, NREL S825 having a lift coefficient of 0.5190, and 0.1869 lift coefficient value is for NREL S834 at wind velocity of 10 meters per second. And for NACA 4412, the lift coefficient value is 0.3467, and for NACA 2412 is the lift coefficient value is 0.1598, and lift coefficient value for NREL S822 is 0.2197. Same for wind velocity of 15 meters per second, 20 meters per second, and 25 meters per second. The lift coefficient values are given for different asymmetric aerofoils, and this graph shows the velocity versus lift coefficient for an asymmetric aerofoil. This graph shows the lift coefficient for NREL S825, and this graph shows the lift coefficient for NACA 4412, and this graph shows the lift coefficient for NREL S822, and this shows the NACA 2412 lift coefficient values. These are the drag versus velocity versus drag coefficient result for asymmetric aerofoils. This table shows the velocity versus drag coefficient for asymmetric aerofoils. If we observe at wind velocity of 5 meters per second, NREL S825 having a lift, having a drag coefficient of 0.185 value, and NREL S834 having a value of 0.0166, and for drag coefficient of NACA 4412 at 5 meter wind velocity of 5 meters per second, the value is 0.162, and the drag coefficient value for NACA 2412 is 0.0153, and drag coefficient value for NREL S822 is 0.0074. Same at drag coefficient value for at wind velocity of 10 meters per second, 15 meters per second, 20 meters per second, and 25 meters per second are given in table. This is the graph for velocity versus drag coefficient. If you observe NREL S825 having a maximum drag coefficient, which is not good. This graph shows the drag coefficient for NACA 4412, and this graph shows the drag coefficient for NREL S834, and this graph shows the drag coefficient for NACA 2412, and this graph shows the drag coefficient for NREL S822. These are the angle of different results for NACA 0012 symmetric aerofoil at different angle of attack. At 50 angle of attack 15 degree, drag coefficient is 0.0212, and lift coefficient is 0.8698. These are the different angle of attack attacks, and these are the drag coefficients for drag coefficient at different angle of attack and lift coefficient value at different angle of attack, but velocity is constant, which is 5 meter per second. And if we observe at this table, at the angle of attack 10 degree, the lift coefficient is maximum for NACA 0012. And we can observe from graph also that the lift coefficient graph is increasing at the 10 angle of attack. At the 10 angle of attack, the lift coefficient is maximum. But if we increase the angle of attack, then the lift coefficient decreases. So the maximum angle of attack, or we can say good angle of attack for NACA 0012 is 10 degree. And this is the drag coefficient for NACA 0012 airfoil. At 10 angle of attack at 10 degree, the drag coefficient is high. And this is the results for NRL S825 at different angle of attacks, and velocity is 5 meter per second. And these are the different angle of attacks, and these are the different coefficient values for at different angle of attack, and these are the lift coefficient value at different angle of attack, but the velocity is constant. And if we observe here also that the lift coefficient value increases with the increase of angle of attack, but there is a point which is angle of attack at 10 degree, the lift coefficient decreases. So from here we can say the best angle of attack for NRL S825 is 10 degree. These are the glide ratio for symmetric airfoils. What's the glide ratio? Actually, glide ratio is the ratio between lift coefficient and the drag coefficient. If the glide ratio is maximum for airfoil, then that airfoil having a best result. That airfoil is considered as good. Here we can observe that at wind velocity of 5 meter per second, NACA 0012 having a 165.57414 of glide ratio value, and for NACA 0009 the glide ratio is minus 9.6703, and for NACA 0018 the glide ratio is 1.0994, and for NACA 0024 the glide ratio is 18.5462, and for NACA 0006 the glide ratio is 32.15. These are the glide ratios for different symmetric airfoils at different wind velocities. If we observe from the graph that the NACA 0012 having a maximum glide ratio, from here we can observe. So the best airfoil from the symmetric series of airfoil is NACA 0012 which is observed from simulation results. This is the glide ratio for asymmetric airfoils. These are the wind velocities value, and these are the different values for different asymmetric airfoils, and these are the glide ratios for different asymmetric airfoils. If we observe at the graph, the glide ratio for NRL S825 is maximum. So therefore we choose NRL S825 for the fabrication purpose, because this having a maximum glide ratio. So the airfoil having maximum glide ratio, then that airfoil is considered to be good. This is the conclusion of our final year project. In this project, we did a complete analysis of 10 different airfoils. From the 10 different airfoils, we conclude that NACA 0012 and NRL S825 have the best coefficient of lift and best glide ratio. Though some airfoils have more glide ratio and lift coefficient than those of selected airfoils, they are unstable. These are the future recommendation of our final year project. To design other type of airfoils and simulate in Ansys software that may give better result as compared to these 10 airfoils. The boundary layer for airfoil simulation should be revised at some angle of attack to improve the simulation accuracy. By studying of a new series of airfoils, someone can extract good results for future wind turbines. The fabricated airfoils can be tested on wind tunnel for practical analysis. These are the references of the papers that we followed throughout this project. Thank you video, and please subscribe Sakar IBA University page.